In this video, we're going to talk about limits and using Sage to compute limits. We'll look at limits graphically and numerically, and then also Sage has a built-in limit command that can compute limits. As you should have seen already in the lecture, the idea of a limit is that the inputs of a function, the x values, approach some fixed given number, and you want to see if the outputs, or the y values, also approach some specific number or not. So let's look at this first example. The function is sine x over x. Notice that f of 0 is not defined because you would get division by 0 here. But we may nevertheless be able to find the limit as x approaches 0 of this function. Even though f of 0 is not defined, the y values might get close to some fixed number when x gets close to 0. So first off, we'll just do this graphically. So here's the graph, the default graph of this thing. And it looks like when x is near 0, the y values are near 1. Okay, so this graph, remember, should have a little hole right here, which Sage doesn't draw. I want to zoom in to confirm that this is indeed the case, so I got a little closer. Instead of -1 to 1 on the x-axis, I'm now -1/4 to 1/4. And again, it still looks like the y values are close to 1 when the x values are close to 0. And you might think this graph hasn't changed at all. It looks the same, though there has been a change. Notice the y-axis here. This is 0.85 up to 1. This one is now 0.99 up to 1. So much narrower range here on the y-axis. Looks like the answer is 1. One more time, I'll zoom in. So -1/10 to 1/10 on the x-axis. Notice the y-axis. See the scientific notation here. This e minus 1 means move the decimal point 1 to the left, so this is 0.9985, and again it still looks like 1. Now this is not proof that the answer is 1. Maybe the answer is just really close to 1, not quite 1, maybe, who knows. But this is at least graphical evidence that the limit is 1. Alright, here's another example. The limit as t approaches 0 of this expression here, and notice again that this function is not defined when t equals 0. You get division by 0, but the limit does exist. And if we look at the graph here, when the t value, that's the input on the horizontal axis, it gets close to 0, it looks like this function does go somewhere. Okay, there's a hole right here. We should have an open circle if we're going to draw this by hand, but it looks like there is a specific y value that this function is near when the t value is close to 0. I'm going to zoom in a little more, and you can start seeing the limitations of Sage's graphing ability. These labels on the y-axis are rounded to the nearest, and it only can display 4 digits here. This e minus 1 says move it over 1. This is 0.1666. 0.1667, and that's about as precise as you can be on here. So if you keep zooming in, here I zoomed in even more. I'm now going from -100th to 100th, and all of these labels are the same. So that's due to rounding. I'm not sure why there's this kind of weird little jump there. Some probably due to round off error, because the t values are so small here. The values that it's trying to plug into this function are very susceptible to rounding error. I think that's why there's this kind of a little wacko-ness going on here. But the best we can do is 0.1667 for our graphical estimate. Alright, example 3. X approaches 4. Again, this function is not defined at x equals 4 because you get division by 0 here. But near x equals 4, here's the graph. So I want to see what happens at 4. So I put my x min at 3 and my x max at 5, so we can see what happens near 4. So here's at 4, and it looks like this function actually does go somewhere. When x is close to 4, the function looks like it's close to 1/4. And here I zoomed in some more. So I changed my x min, 3.9, changed my x max to 4.1. I'm getting closer to 4. Still see the same thing. Looks like I'm still here in the neighborhood of 1/4. Alright, so the graph may be suggestive, it's not a proof, and maybe sometimes from graphs you can't tell exactly, like in our second example because of the rounding error. Or even in this example, is it exactly a quarter or is it just close to a quarter? So you have to figure out where is the y value when x is close to 4, and that means kind of tracing your hand over to here, and you might not be able to tell exactly where that lines up. So we might be able to get perhaps a more precise answer doing it numerically. And by numerically, I just mean to plug in actual x values and see what the y values are and see if they go somewhere. So let's go back to sine x over x. From the graph, it appeared that the limit was 1 as x approaches 0. It might make a difference if x approaches 0 from the left or the right. That's what this means. So I don't know if you covered this yet in the lecture, but this little plus means x approaches 0 from the right or from above. That means x is greater than 0 and gets closer and closer to 0, and we're going to see what this function does. This little minus right up here means x approaches 0 from the left or from below, so x is going to be less than 0. So I'm going to do this right limit first. So this little plus means the values are bigger than 0. So I'm going to just choose a list of x values that get closer and closer to 0 but are bigger than 0. And that's what I have here, 0.1, 0.01, 0.001, etc. Those inputs, the x values, get closer and closer to 0 from the right, from above. And I'm going to look down here at the output, so I'm just going to run this, and here's what comes out. And I'm going to look and see, do these values get closer and closer to somewhere? Yes, it looks like they get closer to 1. So here I have 0.998, 0.99998, and so on. It just gets closer and closer and closer to 1. It looks like the limit is 1. Now, this is kind of just a totally naive approach, manually entering these inputs. I could definitely program the computer to do this. Be much less typing. I could get lots more calculations faster without having to type them all myself. The reason I didn't do that is because I find that it obscures what's going on for the students. They see it as kind of this magic program that just spits out an answer without really understanding what's happening. I think here you can see by just manually typing these in, you can get a better sense of the fact that these x values are approaching 0, and so hopefully this is helpful. It's a little dangerous here to, you can kind of see the pattern. We're just going by a factor of 10 each time, adding a 0 in here. That pattern might be dangerous in certain limits. It might give you the wrong answer because you have such a nice pattern there. But that would have to be a particular kind of limit, and we're not going to see one of those in this class, though I will say just in general it's dangerous to follow such a precise pattern like that. Anyway, that's from the right side. It looks like these are approaching 1. Let's go look at the left side now. So I need a list of numbers that approach 0, get closer and closer to 0, but they're all less than 0. And so in this case I just stick negatives on. To be less than 0 means you're a negative number, and these numbers get progressively closer and closer and closer to 0 from the left. And what happens? It looks like the y values get closer and closer to 1. Of course, as we saw from the graph, this function is symmetric over the y-axis, so of course these are the same numbers as you get from the other side. So from the left, it looks like the limit is 1. From the right, it looks like the limit's 1, so I would conclude that this two-sided limit, the limit as x approaches 0, is indeed 1. Now again, this is not a proof, but it's suggestive. At least this gives us a goal. If we were going to try to prove it, then I would try to prove it's 1 as opposed to anything else. Okay, here's another limit. X approaches 4 for this rational function. And I need a list of numbers that approach 4 from the right. So here I chose 4.1, 4.0, and so on. You can see the pattern. I just add extra zeros in there, and I see what happens to the outputs. 8.1, 8.00, well, but basically 8.01, 001, and so on. These are getting more and more zeros. It looks like these outputs are getting closer and closer to 8. So I would conclude that the limit is 8. Now how about from the left? Now I need a list of numbers that get closer and closer to 4 from the left. Now I can't put minuses on there because negative things wouldn't be anywhere close to 4. So it's a little different from 0. To approach 4 from the left, I'm going to use 3.9 and 3.99 and 3.999 and so on. Just keep adding 9s. Alright, now there's nothing particularly sacred about 9 perhaps, though it seems like the natural choice. It's kind of the symmetric from here. Here this is 4 plus a tenth, 4 plus a hundredth. This is 4 minus a tenth, 4 minus a hundredth. So it's really the same pattern on the other side. Now don't mix these two up. Students in the past sometimes get confused between these two. They will put, instead of putting zeros here, they'll put 1s. 4.1, 4.11, and so on. In fact, here I'll add it in. You're getting kind of confused with the 9s case and say, okay, well, I'll add 1s. Now the problem with this is that this list of numbers is not approaching 4. This is actually getting bigger and bigger. You're adding more and more, and you're not getting closer to 4. You're getting closer to 4 and 1/9, which is 4.1 repeating. That's not what you want. The same thing on the other side. I've seen confusion. Instead of doing 3.999, we'll put zeros in there and just put a 9 at the end and think that's okay. Let's change there. Okay, and so on. I've seen students do this. You're really getting confused with the left and the right examples. This list of numbers is not getting closer to 4. It's getting closer to 3. Okay, so the more zeros you add, the closer and closer this gets to 3, not to 4. So don't confuse these two. We add extra zeros from the right, and it doesn't really matter if you put a 1 on the end. You can put anything on the end, but 1 is kind of the natural choice for me. And here, you're adding more and more numbers. Don't add zeros inside. You're adding 9s to the end. Okay, so try to keep those left and right sides separate. They really are a little bit different looking. But anyway, we have this list of numbers that approach 4 from below, and what happens to the output? 7.9, 7.99, so on. As you trace these numbers down, it looks like the outputs are getting closer and closer to 8. So I would conclude the limit is 8 from the left. So the limit was 8 from the right, it was 8 from the left, so I would conclude the limit is 8 as x approaches 4. Now that's, again, not a proof, but certainly suggestive numerical evidence. Alright, here I have x approaching -1, and so I want to look from the left and right. This is similar to x approaching 4, except it's a little bit reversed. Because you're on the minus side, what's left and what's right is kind of backwards. So here, remember, as x approaches 4, I had 3.9, 3.99, 3.999, etc. That was approaching 4 from below, or from the left. Here, when I add 9s progressively, I'm not approaching from the left, I'm approaching from the right. These are all bigger than -1. Okay, so you're going to do both left limit and right limit, so it's not the hugest deal in the world if you get them backwards, but try to keep your left and right straight. It'll be helpful in the long run. So this is a list of numbers that gets closer and closer to -1. They're all bigger than -1. So approaching -1 from the right. What happens to the outputs? It looks like the outputs are getting closer and closer and closer to 9. So I would conclude the right limit is 9. How about from the left? Now, this is where I'll use the strategy of adding extra zeros in here. This approaches from the left. All of these numbers are less than -1. So again, it's the opposite of what happened as x approaches 4. You had 4.1, 4.01, 4.001, etc. That approached 4 from the right, from above. Here, adding these extra zeros makes this less than -1, so it's actually approaching from the left. It's a little bit reversed. But the outputs give me the same kind of answer. As I go down this list, the outputs look like they're getting closer and closer and closer to 9. So I would guess that the limit from the left is 9. So it's 9 from the right, it's 9 from the left, so the two-sided limit looks like it's 9. And you can actually, that is the right answer. You can confirm that using algebra. Alright, so we did graphical approach, numerical approach. Now let's do the computational approach. Sage has a limit command. It's just limit, L-I-M-I-D, and then parentheses, and then you type the function that you want to take the limit of, and then you put a comma, and this is how you tell it what x approaches. So there's not an arrow on your keyboard for x arrow 0 like it is in our notation, you just use the equal sign. So x equals 0 means x approaches 0. And don't get confused by that. Remember, we're not saying x actually equals 0. That's just the x that we're trying to approach. That's how the limit command was designed. So, limit sine x over x approaches 0 is 1 according to Sage. Now, again, this is not a proof. Just because Sage says it doesn't mean it's automatically true. It's probably right most of the time, but there may be some times when something goes wrong. I don't know. But this is certainly suggestive evidence that the answer is 1. So here I typed sine x over x directly. You could also, if you've previously defined the function, maybe to graph it or do something else with it, you can use the function name in here, just like with all the other Sage commands. Alright, we looked at this one numerically above, and we looked like the answer was 9, and Sage agrees with us. The answer is 9. Be careful typing this fraction into Sage. Notice the parentheses here around the top of the fraction, parentheses around the bottom of the fraction. Okay, you can also compute limits as x approaches infinity or negative infinity, otherwise known as end behavior. You may have not gotten to this quite yet in the lecture, but this just means x approaches infinity means x gets bigger and bigger and bigger without bound. So on the graph, you're just going off to the right-hand side of the graph along the x-axis, just keep going and going and going. Alright, so limit, type in the thing I want to take the limit of, comma, and then you can just put x equals positive infinity here. And it tells me the answer is half. Okay, so you just type out infinity. It doesn't matter if it's lowercase or uppercase I here at the front. Either one's acceptable. You could probably leave off this plus, though I'll tell you in a minute why I put that plus explicitly there. Here's a graph of that function, and you can see what that kind of means graphically. Imagine, x approaches infinity means you just march along this horizontal axis off to the right forever. And you look at this graph and see where does this go. As x gets bigger and bigger and bigger, it flattens out. I've put in this dotted line is the line y equals a half. And you can see this thing just kind of flattens out, getting really close to that line y equals a half. That's a horizontal asymptote for this graph. And that's what these infinite limits mean graphically. If the limit as x approaches infinity is a number, then the function has a horizontal asymptote at that y value. Alright, here's sine x over x again, but we're not looking at x approaching 0, we're looking at x approaching minus infinity. So you just type x equals minus infinity here in the limit. Sage tells us the answer is 0. Let's look at the graph and confirm that. You can see as x approaches minus infinity means you go off to the left on this x-axis forever and ever and ever. And you can see what happens to this thing. These waves are getting shorter and shorter and shorter. So this is kind of collapsing down onto the y-axis. The y-axis here is actually a horizontal asymptote. The further you go out there in the negative x direction, the closer this thing gets to the x-axis. The line y equals 0. Y equals 0 is the x-axis. So you're getting sort of smaller and smaller here, closer and closer to the x-axis. That's our horizontal asymptote. Now a little caution when you're dealing with two-sided limits in particular. Okay, the limit from the left or right, which I'll talk about in a minute, doesn't have the same issue, but two-sided limits have a potential problem when the limits are infinite. And so I want to look at limit as x approaches 0 of 1 over x. And Sage says the answer is infinity. Now, normally we would think infinity means the same thing as positive infinity. It actually doesn't in Sage. Let's look at this graph for a minute. As x approaches 0 from the right, the y values just get bigger and bigger and bigger. There's a vertical asymptote here. The y values just go off to infinity. So we say the limit as x approaches 0 from the right of this function 1 over x is infinity. It is positive infinity. From the left, as x approaches 0 from the left, the y values get smaller and smaller and smaller. This shoots down towards negative infinity. So we say the limit as 1 over x approaches 0 from the left is negative infinity. So from the right, it's positive infinity. From the left, it's negative infinity. Since those left and right limits are different, we would say that the limit doesn't exist at all. So this limit, 1 over x as x approaches 0, we would just say does not exist. Now, infinity and minus infinity don't mean that the limit exists either. But it's a particular way of not existing. So in this case, we would normally say that the limit doesn't exist. Why does Sage say the answer is infinity? Well, the reason is Sage distinguishes between plus infinity and minus infinity, and just plain infinity without a plus or minus. Minus infinity is that left side of the real number line, and plus infinity is the right side of the real number line. Infinity without a plus or minus on it is complex infinity. So complex numbers, involving square roots of negative numbers, those imaginary things. Complex numbers don't live on a line like the real numbers do. Complex numbers live in a plane. And with a plane, there is no right side and left side, so there's no plus or minus. This is kind of a plane here, and you can imagine going off to infinity that way, or go off to infinity that way, or go off to infinity that way, or that way. Whichever way you go, you're going off to some sort of infinity, but there's no plus or minus side. So there's no distinguishing between plus and minus infinity in complex numbers. So if you think of 1 over x as a function living in complex land, there is no difference between going off to plus infinity and going off to minus infinity, and that's why it says the answer is infinity. I know that's a little bit irritating, but that's just how it is. It's always nice to check your answer with a graph, kind of avoid this trouble. Let me talk about one-sided limits in Sage. So to do a limit from the right or from the left, you add the direction, and to do that in Sage, type the limit command. Here's the function. Here's what x is approaching. Then another comma, dir for direction, equals, and then quote plus, or quote minus. Plus is from the right, minus is from the left. In fact, you can actually type out the word right here and the word left here, and it will also work. But this is shorter. Don't forget the quotation marks around the plus, quotation marks around the minus with these directions. So here it says with 1 over x as x approaches 0 from the right, from above, the answer is plus infinity. That's what we saw in the graph. From below, the answer is minus infinity. And that's what we saw from the graph as well. One-side limits often come in handy when you're dealing with piecewise defined functions. Unfortunately, the limit command doesn't work with the piecewise stuff in Sage, at least not yet. Somebody might program it eventually. Maybe one of you would like to volunteer. But anyway, here's a piecewise defined function. It is possible to input these things into Sage, and you can graph them with the regular plot command. So here's how you do it. This is not something you really need to do much of, so I'm not going to talk a lot about this, but if you do need to define a piecewise function in Sage, here's how you can do it. F equals piecewise is the command. Here's the parentheses for beginning that command, and then each of these 3 rules, or however many rules there are, gets brackets around it. Well, first there's the outside brackets for, okay, here's a list of pieces. So a list in Sage always has brackets. So parentheses for the piecewise command, brackets for a list. This bracket is the first list element. The list is this rule for this domain. So first you put the domain. This is interval notation, so minus 5 to 2 is the interval of x values. The rule that applies in that interval is x squared. The interval from 2 to 3, which is this part right here, interval from 2 to 3 has this rule that applies. And the interval from 3 to 5, that's this interval, 3 to 5, has this rule. So there it is. And here's the plot. Notice it inserts these little vertical line segments, which is not correct. I'm not sure why it does that. It didn't always. Piecewise plots didn't used to put those, and somebody changed the program for this to do something, I don't know what, and now it adds these mistakenly. Now, if we want to see the limit as x approaches 2 of this function, we can see it doesn't exist. As we go from the left, it looks like the limit's maybe 4. From the right, as we approach 2, it looks like the limit's maybe 1, and those are different. So it's not approaching a fixed number, it's approaching 2 different numbers depending if you're going from the left or the right. Okay, ignore this little vertical chunk. Now, unfortunately, the limit command doesn't work with the piecewise function If you want to do this in Sage, you're just going to have to kind of manually figure out which rule applies from the left or the right, and then do that. So here, as x approaches 2 from the right, right, that means x is bigger than 2. That means we're looking at this range here, x bigger than 2. So as x approaches 2 from the right, this is the rule that applies. So the limit as x approaches 2 from the right is the limit as x approaches 2 from the right of that particular rule, which is 1. You can do that in Sage, no problem. There it is. From the left, okay, x is less than 2. That's this one. X less than 2, but approaching 2, the rule is x squared. So the limit as x approaches 2 from the left is the limit as x approaches 2 of x squared, and that's 4. You can do that one in Sage. There it is. The limit command can also handle limits involving more than one variable. Don't forget to declare variables other than x if you're going to have other variables. So here, example 13, this is the famous difference quotient you learned to hate in pre-calculus, and when the limit as h approaches 0. This is the definition of the derivative, the main thing in calculus 1. So important calculation here. Really, this is the reason why limits were invented, to deal with this kind of thing. So I declare h to be a variable because there's an h here. H is actually the variable involved in the limit. H approaches 0 here. X is just kind of going along for the ride. X doesn't approach anything. It's fixed. So x is just x. Be careful when you type this, parentheses here around the top of the fraction, okay, because that difference needs to be on top of the fraction. And there's the answer, 2x. Alright, I want to do one last example similar to what you're going to have to do on your assignment. Kind of puts the three different approaches together. So this is x approaches 0 of sine 1 over x. Here's the graphical approach. When x approaches 0, I don't see y approaching anything. I see lots of oscillation. This thing is going up and down, and it just kind of gets lost there. Let's go ahead and zoom in and see if I can see anything better. And the answer is no. I zoom in, and I still just see lots of waves. These waves are getting closer and closer together. In here, it's just oscillating uncontrollably. So it doesn't look like the y values are going any particular place. It suggests the limit doesn't exist. Let's look numerically. So here's a list of numbers approaching 0 from the right. And what happens? Do these y values, the outputs, approach something? No, they flop all over the place. So it changes between plus and minus. The size gets bigger and smaller, alternatively, so they're not going anywhere. It doesn't look like it's approaching anything. How about from the left? Same thing. Okay, here's a list of x values approaching 0 from below. Here's the y values that go with it, and they just are jumping all over the place. It doesn't appear that they're approaching anything in particular. So let's ask Sage. Here's the right limit, here's the left limit, here's the two-sided limit. In all three cases, Sage says IND. IND is an abbreviation for indefinite but bounded. That's one way that Sage tells us the limit does not exist. This happens whenever you have oscillation. There's a bound on the values. Notice that all these y values are stuck between -1 and 1. They never get outside that range. So there's a bound on the y values, but it doesn't approach any sort of fixed thing. So that's what that is. Now it should make some sense algebraically. When x approaches 0, 1 over x approaches plus or minus infinity. Let's go back up to what this function looks like. Okay, x approaches 0, 1 over x is going to approach infinity or negative infinity, depending on if x is less than 0 or greater than 0. And what happens to the sine function as the values inside just get big? Well, sine just flops back and forth between plus or minus 1 forever. It doesn't go anywhere. So that should make some sort of sense that the limit doesn't exist. Okay, we've seen several ways where the limit doesn't exist, and Sage has different kind of outputs. I would like to briefly go through the 5 different possibilities for when a limit doesn't exist. So the first one is und, which is shorthand for undefined. That happens when the left and right limits both exist. Okay, from the left to the right, it's a number, but it's a different number. So that happens, for example, in x divided by absolute value of x, as x approaches 0. And you'll see more about that in your assignment. Und. We saw the ind, indefinite but bounded. That happens when there's oscillation back and forth. There's boundaries, but it doesn't approach any particular number. So that's ind. We also saw infinity, which is the complex infinity. That happens when the left limit's positive infinity, the right limit's negative infinity, or vice versa. So you get opposite infinities from the left and right. That was 1 over x. And then there's positive infinity, where the function actually increases without bound from both left and right. And then negative infinity, the function decreases without bound from both the left and right. So for example, 1 over x squared, in that case, because of the squared, it's similar to 1 over x, but both sides of that function point up. So you get positive infinity. And then minus 1 over x squared, in that case, both branches point down, and you get negative infinity. All of these are examples of the limit not existing. So if this is what you get, if I was going to write down the answer by hand, I would say does not exist. Now in these last two cases, it does not exist in a particular way. We would normally write the limit equals infinity, or the limit equals negative infinity. That doesn't mean the limit exists, it just means it fails to exist in that particular way. Alright, so in your assignment you're going to explore these various limit concepts in Sage from the computational approach, the numerical approach, and then the graphical approach.